I'm Sophie Bates.
My name is Tyler Grimsich.
My name is David Huda.
My name is Bobby Dalton.
I'm Krishna Nagarajan.
I'm Abigail Moser.
I'm Joshua Manowski.
I'm Cole Nielsen.
I'm Abhi Ramaraj Patuni.
I'm Kevin Pothast.
I'm Yash Schmidt.
I'm Christopher G.
I'm Andrzej Zamianov.
I'm Tyler Nord, and we are Team Fahrenheit 535.
This spring, we participated in Dr. Timothee Pourpoint's AAE 535, Propulsion Design Build Test Course.
With the challenge of developing a hypergolic thruster with as much optical accessibility as possible.
The specific requirements of this class were to
use a triglyme sodium borohydride mixture as the fuel,
and rocket-grade hydrogen peroxide as the oxidizer.
Have a firing duration of 1 second.
Provide less than 25 pounds of thrust.
Include a perfectly expanded nozzle.
Operate at a chamber pressure above 200 psia.
Produce a digital twin of the thruster, compare simulated data to actual test results.
And incorporate as many transparent components as possible.
Such a thruster will provide direct imaging of difficult to model fluid systems.
And allow for better informed modeling efforts.
Our team discussed multiple different potential designs for our kit. Eventually, the team went with a one-piece cylindrical fused silica chamber. We had to take into account the thermal expansion coefficients of our chamber material, as well as the expansion of our flanges that we used to compress the chamber in order to properly seal it. We were deciding between a conical nozzle or a contour nozzle. After discussing with the manufacturer, we ended up choosing a conical nozzle as that was much easier and kept manufacturing costs lower.
The biggest concern we had is for thermal shock of our chambers, because that is a common problem. And so what we wanted to do was model both the heat transfer and the thermal stresses along the chamber radially. We're running extremely fuel rich. We have the equivalence ratio of 3.2, and we were able to get a time-dependent temperature gradient across the wall of the chamber, and using that, see are we going to be exceeding the material limits.
The optically accessible components on our test rig are the optically accessible fuel tank, oxidizer orifice, fuel venturi, and the run valve. The oxidizer orifice is an orifice because our diameter is about 40 thousandths of an inch, which is too small for the kinds of machinery and equipment we have here. The fuel side venturis were possible because that formlapse resin is 3D printed, so theoretically we can 3D print any contour.
There are many different ways to design a valve, and many different styles of valves. We settled on a poppet style valve due to its relatively simple linear actuation. We have two different designs, really, a soft poppet and a hard poppet.
We proofed all of our tanks to 500 psi, verifying that the leak rate is acceptable below 0.1 psi per minute. We also raised the internal pressure to 1000 psi to verify that there's no mechanical rupture or significant seal blow-by at those higher pressures. We also cycle tested all of our optically accessible components to evaluate what effects unloading and reloading pressure would have on our components.
For our main hard material we chose, non-optically accessible, we chose both 316 and 304 stainless steel. In terms of optically accessible materials, on triglyme we used acrylic and Formlab extruded up. On the oxidizer side, we used polycarbonate.
A coaxial swirl injector basically produces conical sheets of propellants that essentially break apart and atomize by swirling the fluid inside a swirl chamber and then accelerating it by constricting it to a smaller area. We specifically chose this type of injector for our application for 3 reasons. One is it has very comparable atomization quality characteristics like an extended jet. 2 is because the velocity is composed of 2 components, an axial component and tangential component. You could minimize the axial component for like a short chamber length that we have in our specific application. The 3rd reason we chose the coaxial swirl injector was because its atomization process is hard to model.
When sizing the triplet, we started with getting a diameter ratio between our orifices for maximum mixing efficiency. Then we used an assumed CD and a target M dot and delta P so that we can get our actual areas. As it was our backup option, we were willing to sacrifice the optical accessibility of the triplet in order to improve manufacturability and cost. We ran cold flows on our prototype injectors to validate our discharge coefficients, our mass flow rates, and our atomization through shadowgraphy techniques.
With shadowgraphy, we have the high-power LED passing through our diffuser, and then it's collimated between two lenses. The light is then diffracted, and the shadow or dark spot that is then projected onto the plane is picked up by our high-powered camera.
With shadowgraph, you can see the spray break up a lot better for example, a coaxial swirler. A swirler in and of itself is a very complex injector, so that's something that we wanted to make sure we nailed down off of the stand before we had anything, and we wanted to use this cold flow stand here to image the spray characteristics. So we're looking at the cone angles, we're making sure our cones are impinging, and we're also looking at the atomization, the droplet size.
We got filters for the sodium and the boron byproducts of combustion to be able to look at the flame front as combustion happens. This was important since it is within that visible spectrum, and we wanted to be able to see that within our chamber.
So on a test day, we wore the proper PPE for the specific propellant we were handling. In the case of Triglime, that includes Tyvek suits, boots, nitrile gloves, a face shield, glasses, and a respirator. PPE we used for peroxide included orange rubber suits, boots, nitrile gloves, face shield, and goggles. All valve actuations were handled in the control room via our VI. The only adjustments on the part of the test operators were the manual regulators.
So we found through our chemical compatibility studies that if you want an optically accessible material that's compatible with hydrogen peroxide, your best bet is typically polycarbonate. On the other hand, if you want something that's transparent with a triglime sodium borohydride mixture, you're probably better off using a resin or acrylic. One of the other big things that we did with our propellants is they're both clear. So what we did is we experimented with a couple different types of dyes, and we found out that for peroxide, food coloring with highly artificial ingredients used actually stuck around in there for a very long time and didn't bring down the concentration of that peroxide. And for the fuel, we ended up using a red solvent dye, and these two dyes together allowed us to have a nice red fuel that we could see and a nice blue oxidizer.